Hey, welcome to the second class meeting of EECE451, Introduction to Digital Signal Processing. The first announcement is about homework 1. It is not yet posted, but will be posted by tomorrow. I'm not certain, but by tomorrow. And due will be 1400, which means 2 p.m. on next Tuesday. So before you come to the class meeting, number 3. Here goes the overview of the course. And we are quickly reviewing the key ideas about discrete time signals and systems now. And we will move to Z-transform sampling, blah, blah, blah. And eventually, as I told you, the something completely new would be discrete Fourier transform. And this is the heart of this course. So I hope after this semester, you will have no fear about using discrete Fourier transform to do a lot of things, like to approximate continuous time Fourier transform, to approximate discrete time Fourier transform, and to do some other signal processing. And as I told you, since this DFT is so important, there is a very famous computationally efficient algorithm to perform this transformation, which is called fast Fourier transform. As I told you last time, this fast Fourier transform algorithm can be said fast discrete Fourier transform algorithm. Got it? So as I told you, here goes some simple ideas about to use discrete Fourier transform to do a lot of Fourier analysis. So these are the key, and we are going to use this DFT and other signal processing techniques to do something interesting. For example, I'm not yet sure whether we can reach that part, but there is something strange called Cepstrum. By the way, Cepstrum is not well known, but after you mixing up these characters, it looks like spectrum, right? See that? C, E, P, S, and trum, right? Actually, this terminology Cepstrum is coined by rearranging the characters of the term spectrum. It's very similar to spectrum, but a little bit different. And its use is best found yet far in speech or voice signal processing. Just before I come to this class meeting, I discussed what kind of programming projects would be helpful to you to deepen your understanding of this material covered in this course. I also talked about simple speech compression one, but probably I will skip the compression part, but ask you to synthesize speech signal, giving a filter that models our vocal tract and the input signal that models our vocal cords vibration. And you will find something interesting. For example, you record your voice and decompose your signal, voice signal, into a filter and an input signal. And this input signal is not arbitrary input signal, but in a short period, it's kind of periodic signal if your vocal cord is vibrating. For example, when we make a sound of consonant, 자음 in Korean, then in that case, this input signal looks like a white noise. However, when we speak vowels, 모음, then as you can easily feel, so 2 fingers touch your neck and say then you will feel that something is vibrating in different frequency, right? So let's try. Right? Okay, you don't touch. I remember who didn't touch your neck. Anyway, so interesting thing is like this. If you just change the period or frequency of this periodic impulse, actually you can mimic your, for example, for the male students, your mother's voice signal. For example, my relatives always say that I resembled my mother, which means that I may have similar facial features. Actually, that determines, for example, the structure of our nasal cavity and even the shape of mouth and this tongues and shape of the everything. Now, this is a filter. So actually, my mother and I share the same filter when we speak, for example, mother, right? The difference is that my mother, as a female, may have a little bit smaller air pipe that connects my mouth to my lungs. But as a male, I may have a bigger pipe. Now, suppose you have two vibrating membranes, then which one could be vibrate faster? And in every question like this, in order to have something intuitive, you consider some extreme case. Suppose you have this large air pipe and that large two membrane vibrating. And due to the mass, huge mass, vibration frequency may not be large. But if your pipe is just like a straw for your coffee, then the membrane would be very small, which means that less mass, then it could vibrate faster. Which means that after some leap of faith, my vibrating frequency, even though I say mother, would be lower than my mother's saying mother, right? So interestingly, if you change the frequency, even though I decomposed my voice, but I little bit increase the frequency of this impulse train, which means that reduce the period, and then synthesize. Sometimes I hear my mother's voice. Got it? And or what could you do is that probably a lot of male students has suffered a lot of change when they become an elementary school student to a middle school student when their air pipe becomes larger, right? And then your very cute voice, like 안녕하세요, 교수님, suddenly becomes 안녕하세요, 교수님 type thing, right? And interesting thing is that if you just change the frequency, you may recover your old, cute, little children boy's voice. Anyway, we may do something like that. When we do that, this Cepstrum is very important. So anyway, remember that, okay? There is some strange terminology like Cepstrum, and our professor says that it has been very important when we do voice signal processing. Anyway, and hope, I'm not sure. It's very interesting topic, but main topic is anyway, these things. So keep remember, DFT, FFT, and use of FFT are very, very important and core and heart of this course. Okay, let's review. About the course administration, I told you that you have fixed midterm and final dates. And I'm not going to move that time slot. Sorry about that. And second is that we have two home pages. One is on PLMS, and the other is on my lab homepage. And many of important links, like a handwritten PDF of this course, and also YouTube video link is available only on this secondary homepage. So you'd better go visit the home pages. So let me show you. So you go to cisl.postec. So cisl.postec. And here comes the home page. Okay, something's very, very slow. Yeah, something's wrong. I'm not sure. But anyway, so you click teaching, you click EECE451, you click schedule download, and then there pops up a table where you can find almost everything, like handout for this course, annotated handout, YouTube links. Got it? After the course administration, I immediately started some discussions about digital signal processing. And the first one is this one. We all well know about continuous time signal processing, I hope, because it's covered in signal gen systems and it's one of the prerequisites of this course. So we all know about continuous time signal. And our textbook and many people claim that the real world or physical signal or physical phenomenon, when it is modeled mathematically, needs to be modeled as a continuous time signal. By the way, continuous time is often abbreviated, 축약어, abbreviated to capital C and capital T. So CT signal x of t means mathematically what? The signal's name is x, and its argument, the time index, is any number in the real set, and the value at a specific time instant is a member of real number. So this is a mathematical model of a continuous time signal. However, as I told you, even though in electrical engineering, continuous time signal well models most of the situations, but it's not. As we all know that electrons are quantized. It has finite quantity, right? So the so-called current, the flow of electrons or sometimes holes, is actually not well modeled by a continuous function. And some physicists, I don't know whether they are major group in physics or not, but now claims that even time, our time is quantized. I'm not sure. So in that sense, this model that has domain R and range R may not be so true in modeling our physical or real world. But if there are many electrons involved and many holes involved in our electrical engineering some problem, then in that case, the current may be under some limitation of our measurement equipment, that may be seen as a smooth function of continuous parameter time, right? So in that sense, continuous time signal model well models continuous time signal as a function from R into R may well model a real world, or, but in your extreme case, like suppose you are considering deep space communication. You send Voyager 1 and Voyager 2 around late 1970s, when your parents even were not born or barely born. And that is now traveled more than the distance of the Pluto, which is kicked out of the planet of the sun. But anyway, and it's now in the deep space. And they have, of course, radio wave transmitter and receiver to communicate with the station on Earth. Since the distance is astronomically far, what they say, I do not know, I didn't measure in this space communication, but what they say is that actually they are not receiving electromagnetic wave. They are receiving quantized version of it. Okay, so they count. Okay, we received 3 electromagnetic something. And so this is bit is 0. We received 5, so bit is 1, something like that. Got it? So never forget that in an extreme cases, your model of continuous time signal may fail. Got it? And also now consider not this astronomically large distance, but how to say that? Nanoscale something. Because in electrical engineering, we build very small and also a very less power consuming circuits to do something, to do computation, right? And in that scale, we want to reduce the current because the current is somehow related to the power and energy dissipation. Conversion to heat and just goes away. So we want to build transistors that has less and current. Then what will happen? And some of the physicists in post-doc and also in prestigious other universities, there are groups of people who majored in reducing the size of transistor. So I heard already around 20 years ago, one of the important topic was single molecule transistor. What does that mean? A transistor is made of single molecule, 분자. 한 개의 분자. Can you imagine that? And in that case, probably there are not many electrons. In that case, you may not assume that some current applied to that transistor is a smooth curve. Probably you have to rely on quantum physics or mechanics, where electrons are quantized. So you no longer have some very smooth curve of electrons flow. Got it? So anyway, remember this. Whenever you do something in engineering, we introduce mathematical models. That's the difference between we engineers and scientists from those who major in social science or something, okay? In their case, it's very hard to introduce a mathematical model. Of course, the economists and some business management people, they do very well in mathematical modeling. And you may be surprised to see their research papers. The mathematical skill and level is much higher than most of the electrical engineers. But many people have no such good mathematical modeling. But anyway, what we do is that we engineers or scientists do is that we mathematically model the real world. And we have some objective to do. For example, we want to reduce the size of something. We want to reduce the heat dissipation, something like that. In order to do that, what we need? We need optimization. Optimization requires objective function, which is a mathematical model of real world. Got it? So this is the kind of steps we do. But remember this, whenever we model real world mathematically, our mathematical model has its limitation, its range of applicability. So never forget this. Sometimes your model predicts some good thing will happen. But when you try to make it realize using circuits, it fails again and again and again. In that case, you have to reconsider your mathematical model. Sometimes your model may not work well in that operation range of your work. Due to that reason, you may not get your desired result. Sometimes, even after many failures, still you find that your mathematical model is correct. And in that extreme engineering, something good must be obtained. If you believe that, it could be implemented. Then you just pursue. Okay, if you are head of some department, you believe some mathematical model that may give you world-fast transistor, least power consuming some ASIC chip, then just persuade your team members and say that this is the right way, and let's keep doing it until we success. If your model is wrong, then all the efforts will be useless. But that kind of decision you must make. Got it? Anyway, so remember that mathematical model may not work well or work well, depending on the situation. Got it? So this is the important message. And here goes some important concepts I missed to talk last time. So as you see here, I will use a lot of mathematical notations you've learned from middle school or high school and even in undergraduate school. Something like this, a function named x and that has the domain R and range R, something like that. And in that case here, we have sets. And there are some useful classification about sets. So suppose this is a collection of all sets. The set of sets must be carefully defined. So, and you can divide this group of sets, collection of sets, into two. One is countable. So let me write here, countable sets. So subset of countable sets. And here is the uncountable sets. This is very, very important because this made me different from my high schooler and graduate. Got it? So I hope you have this concept in your mind. For example, uncountable set. What is the representative uncountable set? The set of real numbers denoted by, which one? Is it the color I use? Yeah, sometimes these colors are so confusing. Is it? I believe this one I use. Yeah. So, yeah, the set of real numbers. And of course, the set of complex numbers. They are uncountable sets. And interestingly, for example, the set of real numbers on, for example, this interval is also an uncountable set. Got it? So there are many uncountable sets. And what is a representative countable set? The set of natural numbers and the set of rational numbers, right? And these kind of things. And countable sets are also divided into two. One is countably infinite and finite sets. For example, this is a finite set. Got it? So countability means that actually you can make a one-to-one correspondence between the set of the set and the set of natural numbers. So you can number using natural numbers, number the elements. Got it? And probably some of you who took the introductory element, the analysis course, have found that any rational number can be written in this form with co-prime m and n. And of course, m is not 0. And then what you can do is that you find all the grid points. And what do you do? To assign the natural number to this two-dimensional thing. If I remember correctly, you start, for example, from this one and move to that one and that one and that one, and you do something like this, right? And try to cover all the points in the two dimension. And if 2 points with different m comma m has the same thing, because we have this assumption, then you just drop and number. In that case, you can cover all the two-dimensional points. Each corresponds to a rational number. By doing this, the set of rational numbers is a countable set. And when you count and you can stop at some finite number, then it becomes countably finite set and simply called a finite set. Got it? So this is very, very important in improving your understanding of everything in engineering and science. So the important thing is like this. Even though we call the parameter of this function x as time, sometimes this parameter is just a continuous parameter, not necessarily representing time index. Got it? In that case, we may call x as a continuous parameter signal, not continuous time signal. But in electrical engineering, in many cases, that parameter means time, instant. So we just call continuous time signal. Similarly, here we are talking about discrete time signal. Suppose xd, x sub d, sub means subscript, x sub d may be a function something like this. So it's a function from z into c. Okay, here z is the set of all integers, which is a countably infinite set, and this function, when used, may have this bracket enclosing the index. And this index may mean some time instant. For example, 0, 0.1, 0.2, 0.3 microseconds. However, we usually do is that we only restrict the indices to integers. You may just say that, hey, actually, here n equals, n times some t equals real continuous time. And this is 0.1 microsecond, something like that. In that case, we can always remap our discrete time index to an integer. So this is the convention. Got it? So from now on, whenever we talk about a discrete time signal, the time index would be always an integer. No fraction. Got it? This is the convention most of the electrical engineers agree. Even though physically it may mean some 0.1 microsecond, 0.2 microsecond. Got it? Anyway, this one, when n does not mean or does not involved in computing some quantity related to time, this is called again parameter. And we may call this signal as a discrete parameter signal, as we said this as a continuous parameter signal. This parameter may mean time or not. Got it? However, in most of the cases in this course, our discrete parameter signals index is related to somehow time. So I will just say that here is a discrete time signal. But it's not necessary. Suppose you want to handle something like this. So you have a grayscale image, which means that basically you have a matrix. Suppose 600 rows and 400 columns. And at each pixel, you have a number from 0 to 1. Of course, this 0 to 1 could be any real, but in our digital image processing, usually this is also somehow quantized. So if we assign 8 bits, usually this is all 8 zeros, and this is all 8 ones, something like that. And then, in that case, we have 2 indices. One is representing the row, and one is column. So in this case, this signal, let's say y, may be from what? Something like this. Got it? What does this mean? By the way, this cross is called cross sometimes, or you may say that the set 1 from 600, the Cartesian producted with the next set. Okay, so this is Cartesian product. What does that mean? This entire thing is a set. And this set has what? A pair as an element, and X is a member of this first set, and Y is a member of this second set. Got it? So this means row, and this means column index. In this case, there is no time, right? It just means position. So in that case, we have finite, right? Finite number of possible indices. In that case, there is no time. So you may say that, hey, I have some signal as a matrix signal. And this matrix has the entry having 8 bits, something like that. Okay. So there are many different modeling of real world, or even in electrical engineering. We may use a discrete time signal or continuous time signal. We may use just a single scalar. So as a signal that models real world, electrical engineers use a scalar that could be a real number or a complex number or some member of finite set, and a vector and matrix and a function. And we may call this as a continuous time signal, a sequence. We may call this just simply a discrete time signal. And we may have a sequence of vectors, sequence of matrices. And also we may have, as I told you last time, a polynomial. By the way, in order to represent some discrete time signal, you use the polynomial. Do you remember? Some of you, when you took signal gen systems, the professor covered up to the topic of Z transform. In that case, if you have finite supports discrete time signal, it could be equivalent to a polynomial, right? With a negative exponent or negative or positive, depending on your time origin. But anyway, and also I told you a graph can be used to model a signal. There are many different possible fields and something like that. Among all, we just interested in this one and that one in this course. Got it? So don't be just disappointed that I will not be talking much about image processing or something. We will usually handle these two. Got it? And even for this one, we will convert a continuous time signal to a discrete time signal, and then we process the signal. Because this is the topic of digital signal processing course. Got it? By the way, what's the difference between discrete time signal and digital signal? I asked you last time, and I just mentioned some, and I'm going to talk more about that. The problem is that digital signal is defined differently by different professors in different areas. So there is no single universally agreed definition of a digital signal. Some people in signal processing just say that, hey, there is almost no difference between discrete time signal and digital signal. But in circuits, professor will say that discrete digital signal is modeled as a sequence of numbers. No. Digital signal is an analog signal, but actually it has desirably finite number of levels or something like that. So don't be confused. Anyway, digital signal processing is related to discrete time signal processing. And we need something more to say digital. And the difference is this one. So being digital, by the way, there was a famous book entitled Being Digital in 1980s. And this book, written by some American writer, translated into Korean and published it. Can you imagine the translated title? Being Digital. 디지털이다. So it was so shocking. The title of a book was 디지털이다. Well, anyway, being digital. And the key is that we use bits. As I told you, bit is an abbreviation of binary digit, similar to the decimal number, 십진수. So in order to talk about digital signal processing, anyway, we need to eventually, even though when we talk about discrete time signal, the range is what? R or C in most of cases. So we just handle what? The sequence of real or complex numbers. However, there is another additional process to convert this real or complex number into a vector of bits, right? But in most of the cases in this course, we will not talk about that because that is less fundamental. I'm not saying that it's not fundamental. It's less fundamental than we learning discrete time signal process. So here goes the thing I want to say. So from continuous time signal to discrete time signal to digital signal, okay? There are many ways from conversion from the first step to second step and also second to third step. There are mathematically very different possible strategies for these conversions. But in this course, and most of the cases, what we do is something like this. Suppose you have a continuous time signal x. So it's basically a function from R into R. And we obtain our discrete time signal by just evaluating at every integer multiple of some finite fixed period capital T sub C, T sub S. Got it? And from discrete time signal to digital signal, what we do is that we apply so-called scalar quantizer to this one. And what does this scalar quantizer do is, where it is? I remember I have drawn, yeah. Anyway, so it's like this. Here goes your discrete time signal's value. And what you do is that you have some step function. And sometimes it's flattened, okay? And suppose you have from this to that, you have 16 levels. Then this becomes y sub d. Got it? And for example, you assign 4 zeros here and 4 ones here. That is what? That is encoder. So first, xd to yd. This is called scalar quantization, or the system does this is called scalar quantizer. And then this quantized signal. For example, this may be some number 15, and then maybe some number 14.5. And then this may be 1 or this may be -1, depending on our slope. And then there would be how many? So 16 steps, 15. It's always confusing. But anyway, you know how to compute this delta. But anyway, so the number that corresponds to this flat area may be converted, maybe representing this number output at the quantizer, scalar quantizer, but you need encoder. Okay, so this -1 is encoded to 4 ones, something like that. So this is done actually by so-called analog to digital converter. So analog to digital converter is assumed when we obtain a digital signal from a continuous time signal in this course. And we are going to mathematically model the first step to second step. So continuous time to discrete time. Most of the cases, we do not talk about this quantization and binary encoding. We will only talk about this uniformly sampled version of the continuous time signal. So this is the focus, okay? I'm not saying that these are not fundamental. These are very, very important. Probably some of you remember recent article about DeepSeek by a Chinese company. And they wanted to reduce the number of bits in computing in the computation inside the AI ML model. If you reduce the number of bits, you reduce the computation time. You reduce the power consumption, dissipation. You can reduce the cost, everything. Got it? So it's important, but I say that in this course, this is more fundamental. Got it? So it's unfortunate that I cannot cover all the topics, but just the time allowed to one semester does not cover all the topics which are important. These are important, but I will focus on this. Got it? So let me briefly summarize this part. So in this course, we will first convert a continuous time signal, assuming that is already given, to a discrete time signal by uniformly sampling the signal. And in many real world, the discrete time signal mathematically, conceptually, is quantized and bit encoded. That part is not much discussed. Got it? By the way, even for this uniform sampling, probably your textbook and many of other textbooks in undergraduate level will just say sampling or the system as sampler. The reason why I emphasize this uniform, the adjective, is that there are, of course, non-uniform sampling method. Got it? However, that topic is much more advanced than uniform sampling. So in our conversion from continuous time to discrete time, we will have only one sampling period. Got it? And another one is that, again, here, many of the undergraduate level textbooks just say we have a quantizer. They rarely say we have a scalar quantizer. But I put the adjective. Why? Because there are vector quantizers. That performs vector quantization. And vector quantization is much more fundamental. And scalar quantization is a kind of simplification or some very special case quantizer. Got it? So some of you may take information theory this semester or have taken information theory last semester or next semester. In information theory, when you compressed some signal modeled as a random something, the optimal compressor is usually a vector quantizer. Got it? Let me just cover that part. Okay, about encoding, there are a lot of things I need to talk, but I will skip that. I'm not an expert and not even close to 100 kilometers close to the expert level. So anyway, so you may say that, hey, I have a very big ambition on learning about digital signal processing, and professor discourages me in the second class, saying that, okay, this is the big picture, and I will talk about that one. Sorry, that is the truth. Got it? So there are many things. you will learn and you need to know to become an expert. And now you are mostly seniors and graduate students, and you know that the important truth. First, when you are about to graduate the undergraduates, you believe that you know almost everything in electrical and computer engineering. So, about to get BSEE. Now you become a master's program student, and when you're about to get MSEE, Master of Science in Electrical Engineering, you find usually that you know nothing. Okay? You don't know anything, even in your major. And when you're about to get a PhD in electrical engineering, let me speak in Korean. 뭘 알게 되냐면요. 내가 여전히, 그러니까 박사예요, 곧. 내일 졸업식이에요. 내가 여전히 아무것도 모른다는 사실을 다른 사람이 모른다는 것을 알게 돼요. Got it? It's very difficult to speak in English, so I spoke in Korean. What does that mean? We can never know everything, but we become an expert in very small, specific thing. Especially graduate school is a path to become an expert in a very, 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 very small, tiny topic. And sometimes your PhD thesis topic may be useless. Even though you, for example, publish your result in Nature or Cell or Science, your citation until you die may never exceed 10. Then is your life wasted or useless? No. You learned how to become an expert in some area or topic by paving the way from undergraduate to PhD. So what you do is that after you getting the degree, especially PhD, you have experienced the one path. Now you are given a new topic. Then you know how to improve yourself to become an expert in that area. That is the worth, or that is the value of the graduate study, especially PhD study. Got it? So some of you graduate students may now have been frustrated because you are approaching to graduate, getting master's degree. You now become to know that you know nothing in electrical engineering. But don't be frustrated, okay? You will eventually know that nobody knows you still do not know anything when you get the PhD. But what is important is that you know how to become a PhD level after you're getting a PhD degree. So you can become an expert in any area. Got it? Yeah. So anyway, so in this course, we are teaching very core of digital signal processing. So your project may not be that, how to say that, that's satisfactory in the sense that, for example, you wanted to develop some AI machine learning model that processes the stock market, Korean stock market indices. And then after this semester, you write some Python code. And if you enter and link that code to your stock market account, then suddenly in 2 years, you become a trillionaire. Unfortunately, that may not happen. But I'm going to give you some little idea about to do that. Got it? My TA and I'm preparing some projects related to that. And also, some of the projects would be you write your own code that generates a GIF file. GIF file is the simplest form of the moving picture file, right? And you will learn some at the end of this course, and I hope. Anyway, so I've just said that there are many sampling methods other than uniform sampling, and these are called non-uniform sampling. And there are not only scalar quantization, but also vector quantization. So please remember that. And this picture summarizes visually. And some of you already know that. I always say that the simplification and visualization is very important. So there is a real world or physical world. And usually what we first think is analog signal or continuous time signal or continuous parameter signal. And then we have digital signal, but actually in this course, we limit our interest to discrete time signal or discrete parameters. Got it? Okay, then why we do digital signal processing? So I summarized here. The reason why we do being digital is what? Here, the key is computation. Our artificial intelligence actually is not intelligence we have. Okay, we have natural intelligence. But in this world of AI, actually artificial intelligence is not artificial intelligence. It's a computational intelligence. Got it? So what we do is that our machines are just to do computation. It mimics some creativity, but it does computation. And computation is basically what? Addition, multiplication, and those things. Even multiplication, as you know, is that in digital domain, it could be replaced by what? XOR or binary addition, and or just shifting the information 0 or 1s memorized in some cells of our memory to the next one. Probably you learned about how we develop, how we perform arithmetics using some memory cells and just simple commands like move and XOR or something like that. That's what we learned in electrical and computer engineering, right? So by doing that, we actually, through this path of undergraduate courses in electrical and computer engineering, we learned how to do computation using circuits and computers, right? And now our circuits and computers become faster and faster. So we can compute many things in a fraction of time, or it's just a millionth, it's a fraction of time. That with very small energy. That enabled what? Every day, faster and more efficient computation becomes possible, and they enables computational intelligence very practical now. When I was an undergraduate student, once I wanted to do AI research, and everybody just discouraged me. Hey, Junho, don't do AI or something. You will be starved to death. Why don't you do communications, which looks promising? And I followed their advice. Of course, they include my parents and said, hey, father, I want to do artificial intelligence, but it seems that there are not many professors who has enough funds. Hey, Junho, are you went abroad to do the communications? Yes, and then I'm here. Anyway, so world has changed. Your friends in the other side of building improves the speed of transistors every day, right? And that makes computational intelligence really practical and very inexpensive. And we are living wonderful world, actually. And digital signal processing is actually part of it. You may know some GPUs. Actually, they do what? Digital signal processing. Okay? Of course, circuit guys say that the credits are theirs, but actually it is not. There are a lot of parallel processing algorithms developed by electrical and computer engineers who know nothing about transistors, actually. When I was a graduate student, one of my senior Korean students was majoring in parallel processing. So in order to reduce the computation time, people wanted to parallelize some computation. For example, suppose you have a very large matrix times very long vector. And you know that in order to obtain the first entry of the output, just you multiply first row and this vector. All the other rows are not involved. So if you have parallel processes, that just computes each output entry, then you can reduce the time, right? That is the simplest idea of parallel processing. Of course, the current one is much more complicated. But anyway, so I met a Korean who was about to graduate, getting PhD in parallel processing. And he said that, Junho, I have a big problem. Why? There is not much job here. And he did some postdoc, and he joined some university as a research professor. And then he changed his major into semiconductor. Why? There is no job in Korea at that time. And then the semiconductor companies like Samsung and SK, at that time Hyundai, loved his work because they also wanted to reduce the number of time in, for example, fetching the memory from the cells, something like that. And now, actually, he's a professor in Seoul National University, and his major is semiconductor. And I cannot believe that. He knew nothing about transistor at that time. Got it? So what I'm saying is like this. Signal processing, parallel processing is a part of signal processing. It's very important thing in current GPU circuits and this computational intelligence. And that has foundation in digital signal processing. So just don't too much discourage it by my first two class meetings. Okay, so we are done here. Again, the textbook talks about the pros in Korean 장점 and cons 단점. So the pros of digital signal processing over analog signal processing, or you may say that this is just a discrete time signal processing, and this is continuous time signal processing. So these two things has more flexibility, and you will see what does that mean, and less complexity in many cases, and it may improve the speed, it may improve the precision in computation, something like that. Not only in computing the precision in computation, but it makes also our product, electrical system, it could be computer or chip, much more robust to the production variation. The production line may have some uncertainty in the parameter. But when we produce the electrical systems, analog circuits may not be that robust to that production variation. But digital processes are known to be much more robust. However, still the analog circuit is very important. For example, some people say that, especially in this era of artificial intelligence, we have nonlinear activation function in our neural nets. And nonlinear activation functions have some strange function look like that. And in order to do some mapping like this, with function like its graph like this, we need a lot of information to be stored. But what analog circuit guys say that the simple analog circuit may map this nonlinear mapping very, very easily. So still, analog circuits survives and also very, very important. Interesting thing is like this. In the US, when I was a graduate student, the popularity of analog circuit research was just going down. It's like some Korean students just got abroad and say that, hey, I want to do analog circuits. No, don't do that. Okay, you will have no job. However, in Korea, due to our industry structure, analog circuit has been, and up until now, has been very, very important. And interestingly, many researchers who did analog circuits actually contributed a lot to SK Hynix's success in HBM, actually. Got it? So nobody knows. So even though I strongly support the digital signal processing, but still analog signal processing and analog circuits are very, very important. So you never know, okay? Anyway, here goes some DSP, digital signal processing applications, communications. I'm in this. And radar, actually, this is related to radio ranging and detection. See that? Sorry, radio ranging and detection. Detection and ranging. Okay, so where is the, okay, radar, yeah, something like that, yeah. Anyway, you know that, right? So, and also image processing, speech processing, as I told you, and data storage, medical imaging, medical video these days, and of course, control, financial engineering, and so much more. Got it? So it's important. That's what I want to say. And here goes the digital signal processing history. And in the early stage, we barely had digital circuits, but people already knew the importance of it. And they have found interesting theories related to digital signal processing. And probably many of you have already seen in signal gen systems, Z transform and discrete time Fourier transform, of course, Fourier series, are very, very, very powerful. So we study the theory. And of course, as I told you, DFT, discrete Fourier transform, is very important. DTFT, discrete time Fourier transform, accepts a discrete time signal and generates a periodic signal with period 1. Okay? This is a function of f, which means hertz. And DFT, discrete Fourier transform, accepts a vector of finite length and generates another vector of the same length. Got it? So they are different. Okay? Different mapping. Completely different. Okay? See that? This accepts what? A sequence. Not just the nth entry, the sequence, entire sequence. Okay? But this admits only a vector of finite length. Anyway, and this DFT had very fast algorithm to compute and called FFT. Okay? And this FFT now is used almost every signal processor because it's so powerful. Sometimes we intentionally apply FFT to a vector, even though it seems that that is not necessary. And then we process and we do inverse FFT. And sometimes that is much more efficient and understand straightforwardly than just doing in vector matrix multiplication. And also, this computation becomes possible, very fast real-world FFT possible, with very large input size due to the development of this digital circuit. So there are two buildings in electrical engineering. One building does what? Theoretical research. The other building does what? Enable this theory possible. So they build the circuits. Some people just major in transistor. Some people just major in optical something. However, as a group, what they do is that they are building something. And we do what? We find something interesting, something useful, if that is done by electronic components, electrical components. Got it? Okay, so sound processing, image processing on pixels, image processing in frequency domain, video, stock market. Okay, a lot of redundant terms. Okay, here goes some figures from the textbook. So we are now doing section 2.1, discrete time signals. And here goes what? This is not a discrete time signal. This is what? This is a visualization of a graph of a function. So let me give you terms of function. The graph of a function and illustration of the graph. These are actually different, but our Korean math education was not pursuing that accuracy. So here is a function x from z into r. Now we have a graph. What is a graph, by the way? Graph is a mathematically a set. Okay. So what? Let me just say this one. X and let me say y, z here. It's confusing. Let me see. M, N, A, B. Okay, A, B. Okay, got it. Got it? So graph is simply set of two entities. The first one is what? This index. Let me say just N. Okay. A lot of confusing things. Okay. N, X, N. Got it? So graph is a set of points. Now, if we visualize, then what? It's an illustration of the graph. And this is what? This is an illustration of this graph of this function. But anyway, I will just say that this is a DT signal, even though it's an illustration of the graph of the function which is used to model a discrete time signal. Anyway, got it? So this is the convention, and this is very confusing because what does these lines mean? Actually, they do not mean anything. Okay? If I was the dictator who first wrote the DSP textbook and the dominating in the world, probably I would have said that, hey, remove this one. Whenever you visualize or illustrate a discrete time signal. Why? According to this idea, see that you have the set of points, and first index means some number represented by the points in the horizontal, and the other is in vertical. So I would love this one without the line. The problem is that what? Sometimes when you visualize, this space is so small and it's hard to know which one you don't know. That's why we just put what? Put the lines. Okay. And in your MATLAB, you have a function called stem. And stem is confusing because stem actually does not generate this curve. Stem shows unfilled circles. Something like that. Okay. Anyway, as I told you, see that? these are mathematically well defined. Nobody argues. However, there are many different ways of illustrating a graph. That's why there are different figures. Ready? But most of the textbooks love to use field, okay? Field circles. However, our MATLAB has function called stem, and that use unfilled circles with, of course, vertical bars. Got it? So it's not incorrect to just use, for example, MATLAB plot command, and you just do not connect each point. That's okay, right? Anyway, so this is an illustration, and we are going to use it like this. See that? Now you understand what does this mean. The vertical line is just for convenience. And you may say that, hey, it's obvious why the professor spends so much time. Because it was confusing to me. When I was an undergraduate student, I could not just understand why there is a vertical line. Yeah, I was so stupid like that. Okay, anyway, so suppose this is our measurement, some analog signal, and this spans for 32 milliseconds. And we may have some sampling period, very small, and we evaluate this function at each sampling instant. And then we have this discrete time signal. But be careful, we intentionally just illustrated this discrete time signal so that the two adjacent points exactly matches the time in millisecond to this function. So sometimes you have to intentionally scale the horizontal axis to put these two curves side by side. Ready? So here it says 32 milliseconds, and you have 256 samples. Ready? By the way, sometimes we set 0 just for convenience. Okay? Sometimes, not every time, but sometimes it's obvious. There is no confusion or no argument about selecting that time origin 0. However, in many cases, many other cases, there is no reason why some sampling instant converted to time 0 in the discrete time parameter. And this may sound not that important, but actually, if you do some real-time processing, it's very, very important. For example, you want to build some controller, digital controller that controls the rocket, like SpaceX something. And this one time index shifted may give you total disaster in the launch pad, because your system must act very fast in an extremely fast speed. Ready? Anyway, so how many seconds do we have? Oh, it's already. Okay. So, yeah, this in many cases is just chosen for convenience. Okay, that's all for the day. And you may say that, hey, it seems that there is no programming homework because we covered so little, but I will disappoint you. Okay, that's all for the day.